Assalamu alaikum. We know a long, closely wound helical coil is referred as solenoid. When we pass current through a solenoid, they produces uniform magnetic field along their axis. The coils that I hold in my hand are nothing but solenoids. In this video, we are going to get the expression for mutual inductance between two long coaxial solenoids. For that, I consider two solenoids placed one inside the another. This is one solenoid. It has got a number of turns. The solenoid has got a number of turns. There is one more solenoid is taken, which is placed inside the first one, or something like this. Okay. These are the solenoids. We have taken two solenoids. One is placed inside the another one. Okay, the first solenoid has got a N1 number of turns. N1 number of turns. And its length is nothing but N. Then the area of cross section of the first solenoid is found to be equal to A1. What is the case? The number of turns per unit length is taken as turn density, and it is represented by letter N1, small n1. So these are the parameters compared to the first solenoid. Whereas the second solenoid is found to have N2 number of turns. N2 number of turns, and its length is nothing but small n. Now from the parameter you may find that both the solenoids have same length. And here area of cross section of second solenoid is A2, and the turn density is N2. The turn density represents number of turns per unit length of the given solenoid. So from the parameter it is clear that both have the same length, but area of cross section, number of turns are different. Through first solenoid we pass current I1. Through solenoid 2 we pass current I2. Okay. Here the area of cross section of this solenoid is found to be A1, and the area of cross section of the second solenoid is found to be A2. Okay, remember this. Now, current I1 flows through the first solenoid. We know whenever current is passed through a conductor, it produces magnetic field. The same thing happens with the solenoid as well. When you pass current I1 through solenoid 1, it produces magnetic field around it. That magnetic field is represented by letter B1, and it is found to be the product of a mu naught, number of turns, the turn density N1, and current I1 flowing through the first solenoid. This is the expression for magnetic field produced by the solenoid to the flow of current through it. Okay. About this we have learned long ago. I have made a separate video on this. To get more information, kindly watch that video. Okay. Now, as there is a magnetic field, this magnetic field will have magnetic field lines, and these magnetic field lines will link with the turns of a second solenoid. Hence, it is referred as magnetic flux. So, the magnetic flux linked with each turn of a second solenoid is referred as 5 to 1. So, what does it represent? It shows that the magnetic flux linked with each turn of solenoid 2 due to the flow of current in solenoid 1. This is what it means. And it is found to be equal to the integral of B1 vector dot dA vector. Here I have taken A as a common. It actually represents A2. So area A2. It is nothing but the area of a second solenoid. This is a vector. Okay. Now this is a constant, so it is taken out of integration. Then it is written this way: dA vector. We know when we integrate this kind of term, suppose I have a integral of dx. If I integrate this, d will get cancelled, and what do I obtain is nothing but dx. The similar way, if I integrate dA, I will get a. So in the next step, what do I get is something but this: b1 vector on integration becomes a vector. But here A represents A2, as I told you earlier, so it is written as A2 vector. We know when two vectors are in dot product, suppose here I have A vector dot B vector. They are in a dot product, then they can be written as AB cos of theta. Theta is the angle between A and B. In such a way, the above expression can be written as B1 A2 cos of angle theta. Here, theta is the angle between magnetic field and area of a second solenoid. And it is found to be 0. The angle, the theta is found to be 0. So I write D1 A2 cos of 0. We know cos of 0 is nothing but 1. So what I get is nothing but this B1 multiplied with A2. This is the magnetic flux linked with the turns of second solenoid to the flow of current in the first solenoid. Okay, so 5 to 1 is equal to B1 multiplied with A2. Okay, and it is taken as equation number 1. What is the case? The total magnetic flux linked with the second solenoid can be obtained if you multiply the magnetic flux linked with each turn of the solenoid with a total number of turns. The total number of turns present in the second solenoid is N2. So to get the total magnetic flux, I multiply equation 1 with the number of turns in the second solenoid. This is N2. When I do certain changes to the terms in left hand side, I have to make the same changes to the terms present in right hand side in an equation. So I multiply N2 on the right hand side as well. The remaining terms are written as such: B1 A2. And here I told you earlier, N2 is the number of turns present per unit length of a given solenoid. Otherwise it is known as turn density. By keeping that in mind, right, N2 equals to number of turns per unit length. So from this, N2 equals to capital N2 equals to small n2 multiplied with the L, small l. Okay, so this is written as N2 multiplied with L B1 A2. So the next step, write this one as capital N2 5 to 1 so to be equal to N2 L B1 A2. Fine. I take this one as equation number 2. Now I am going to substitute the value. It's not 2, it is 3. This one is taken as 2. And this represents the equation number 3. Okay. Now I am going to substitute the value of B1 from equation number 1 in a 3. Substituting 1 in a 3. If I do so, what I'll get? I'll get this. Into 5 to 1 is found to be equal to N2 L. In place of B1, I write mu naught N1 I1 A2. Okay, I'll rearrange this one. I'll write it this manner. N2 5 to 1 plus mu naught N1 N2 I1 L A2. This is the total magnetic flux linked with the second solenoid. I box this for better visibility. Then I name this one as equation number 4. Now I proceed. Whatever I have done with the second solenoid, I am going to find out all those terms with the related with the first solenoid. Okay. Now we pass current I2 through solenoid 2. When you pass current I2 through solenoid 2, it produces magnetic field around it. And this magnetic field will have magnetic field lines. The magnetic field lines will be present along the axis of the second solenoid. Now in this region, the region present outside the solenoid will have a magnetic field almost equal to 0. So this region, this area A2 is the effective area when we deal with this case. Okay. So the part of the coil which comes across this area alone found to be present in the magnetic field produced by the flow of current in the second solenoid. So area A2 is the effective area for solenoid 1. Clear? So when we pass current through solenoid 2, it produces magnetic field, and that magnetic field is represented by letter B2. No? And is found to be equal to the product of mu naught N2 I2. So we have done this similar to equation number 1, and it is taken as equation number 5. It represents the magnetic field produced by the solenoid 2 due to the flow of current I2 through it. Okay. The next, this magnetic field will have magnetic field lines. So it links with the solenoid 1. Okay, the turns of solenoid 1, and it is found to be equal to 5, 1, 2. Here 5, 1, 2 represent that magnetic flux linked with each turn of solenoid 1 due to the flow of current in solenoid 2. That is equal to integral of B2. Here B1, so here B2. Then dot dA vector. Now this time I told you effective area is taken to be A2, not A1. No, because outside the solenoid 2, the magnetic field is almost 0. So it is taken that way. Now, follow the same method. I'm going to integrate this B2 vector, integral of dA vector, effective area is A2. Now, I integrate this by following the same method. When I integrate a dA vector, it becomes, this comes as such, and it becomes a A, and it represents a A2, written as A2 vector. Then after that, dot product of vectors is written as B2 A2 cos of angle between them. Here theta is the angle between magnetic field and area, and it is found to be 0. So the next system I write B2 A2 cos of 0. So here cos of 0 gives the value equal to 1. So phi 1 2 is found to be equal to B2 multiplied with A2. Okay, I box this for better visibility so that it can be used further. Okay, I name this as equation number 6. Now I am going to find out the total magnetic flux linked with solenoid 1. Okay, for that I am going to multiply equation 6 with number of turns present in the solenoid 1. What is that? The number of turns present in solenoid 1 is something but capital N1. When this is multiplied with the magnetic flux linked with each turn of a solenoid 1 due to the flow of current in solenoid 2, I get this. See, when I multiply the term present in the left hand side with N1, the same thing I have to do with the terms present in right hand side as well. So N1 B2 A2. It is equal to here N1. Here N1 is nothing but number of turns present in solenoid 1. I am going to relate this with the turn density. Here N1 the turn density of solenoid 1, that is found to be equal to number of turns present per unit length of a solenoid 1. When I cross multiply, capital N1 is found to be equal to small n1 multiplied with small n. Clear? So I read it like this: small n1 multiplied with l B2 A2. Now I know the value of B2. That I will substitute here. I name this one as equation number 7. The substitute 5 in 7. 5 in 7. If you do so, what I get this. See? N1 5 1 2 we found to be equal to N1 L. Value of B2 is nothing but mu naught N2 I2, and we have E. Okay, so I rearrange this. If I rearrange this, what I'll get? I'll get N1 5 1 2 is found to be equal to mu naught N1 N2 multiplied with the current flowing through it. That is nothing but I2. The current flowing through this one is I2. After that, what is the left here? It's L. L A2. So this is the value of the total magnetic flux linked with the first solenoid. Okay, I box this. And it is named as equation number 8. Equation number 8. Now, equation number 4 gives us the total magnetic flux linked with solenoid 2, and equation 8 gives us the total magnetic flux linked with solenoid 1. Here our aim is to get the expression for mutual inductance between these are two solenoids. So we know that the magnetic flux linked with a coil. Now I take this magnetic flux first. 5 to 1 N2 5 to 1 is the magnetic flux linked with the second solenoid. Now this is found to be equal to the current I1 passing through the first solenoid. Now, if it is so, when I remove this proportionality, I have to include a constant called as the proportionality constant. And this equation will turn into appear something like this: N2 5 to 1 equals to a constant. This constant calls proportionality constant. Then write I1 here as such. In the place of this proportionality constant, I mention M 2 1. This is the proportionality constant, and it is nothing but mutual inductance. Mutual inductance of solenoid 2 with respect to solenoid 1. Okay, multiplied with the I1. So I box this. This is taken as equation 9. Okay. Now I'm going to compare equation 9 with the equation 4. Is compared with equation 4. Comparing nine and 4. Why do we do so? If you look at these two equations, 9 and 4, you'll find that both of them have the same term in the left hand side. So they are compared. If we do so, then what we get is something like this. We get M2 1 multiplied with I1 equals to the term present in the right hand side of equation 4. Mu naught N1 N2 I1 L A2. Okay, now here this I1 and this I1 get cancelled. And what do we get at the end? It's nothing but this. M21 is equal to mu naught N1 N2 L A2. This is the mutual inductance of a solenoid 2 with respect to solenoid 1. Okay, I box this. Now I take this as equation number 10. Now I'm going to repeat the same method, and I'll find out the value of M12, which represents the mutual inductance of a solenoid 1 with respect to solenoid 2, by following the same method. Let's find out the value of M12. Now I write that one here, this side. To get the value of M12, I follow the same method. So the total magnetic flux linked with the solenoid 1 with the flow of current in solenoid 2 is nothing but N1 512, and it is found to be equal to, and is found to be directly proportional to the current flowing through solenoid 2. So it is plus N1 512 directly proportional to I2. Here I remove proportionality. So what I will get if I do so like this, N1 512 no, and put equal to sign here along with a constant. Now this we do when we remove proportionality, okay, and I2 is written beside it. Now I name this constant as M12. This is N1 512 equals to M12 multiplied with the I2. Here M12 is nothing but mutual inductance of a solenoid 1 with respect to solenoid 2. So the next step, write this here, I2 equal to M1 2 I2. I name this one as equation number 11. Okay. Now I'm going to compare this with the equation 9. I'll compare this with the not equation 9, it's compared with equation number 8. Sorry. So comparing. The reason is if you compare 8 and 11, you'll find that both of them have the same term on left hand side. So they are compared. Comparing equation 8 with the 11. So what I'll get? So if I do so, I'll get this. Here M1 2 becomes equal to this present on the right side of the equation number 8. Is that mu naught N1 N2 I2 L multiplied with A2. Okay, these are right here. And before doing so, see the common terms. There are I2, this I2 and this I2 get cancelled. What do I obtain is nothing but M1 2 found to be equal to mu naught N1 N2 L A2. I box this for better visibility. This is the value of mutual inductance of solenoid 1 compared to with respect to solenoid 2. I name this one as equation number 12. Now if you compare equation 10 and 12, you will find that in both equations the term present in the right hand side is same. Comparing ten and 12, equation 12. What do you get? You get this. M1, 2 is found to be equal to M2, 1, and these two are found to be equal to mu naught N1, N2, L multiplied with A2. Okay, so these two terms have got the same value, so they are replaced with a common term, let's say M, which represents the mutual inductance between these two coaxial solenoids. So at the end, I write this as M equal to mu naught multiplied with N1, N2, LA2. Okay. This is the final expression which provides us the value of mutual inductance between these two solenoids placed in the common axis, one inside the another. And here, suppose these solenoids are placed in a medium of a relative permeability mu r, then this equation can be written as M. Here, this can be written as in a medium of a relative permeability mu r. This can be written as M equals to mu multiplied with N1, N2, L, A, 2. And here we know very well the relation between relative permeability and permeability of free space is nothing but this. Mu r is equal to mu upon mu naught. The permeability of a medium, this is permeability of free space. Okay, the ratio of these two provides us relative permeability. By keeping this in mind, if we cross multiply, what we get is nothing but this. Mu is found to be equal to mu naught multiplied with mu r. Yeah, this I am going to use here. This I will use here. See what I will get if I do so. Get this value to be equal to M equals to mu naught mu r multiplied with N1, N2, L, A, 2. This is the expression for mutual inductance between two solenoids placed in the common axis in a medium with a permeability mu. Clear? I hope the video is useful. If you have any kind of doubt related to that topic, can you put your question in the comment section. Thanks for watching.